So let us continue our learning of the subject Advanced Machine Learning. Today's topic under discussion is support vector machine. So we'll be directly using the prescribed textbook. Uh, which one is that? Jason Browley's book, Master Machine Learning Algorithms. Discover how they work and implement them from scratch. So this is the textbook I was referring to by Jason Browley. And today's topic under discussion is support vector machines. Okay.
Okay.
The short form for support vector machines is SVM, which is a machine learning algorithm, very well-known algorithm and high-performing algorithm with very less tuning. Now, we need to understand the term maximal margin classifier here. Okay, what is this? It's a classifier. It's a hypothetical classifier. Let us say we have an input x, input variable x, okay, in an n-dimensional space. But let us say you have two input variables. Then our plane becomes two-dimensional space. A hyperplane is a term, is a line that will be splitting these input variable space, okay. The hyperplane is selected in such a way that will be separating the points in the input variable space by their class, either class 0 or class 1. So in this two-dimensional space, we can visualize a line with this formula b0 plus b1x1 plus b2x2 is equal to 0, where you know that b1 and b2 are the coefficients which are slope of the line and b0 is the intercept of the line, while x1, x2 are the two input variables. Classification is achieved by using this line. Suppose your point is above or below line, what happens? If the point is above the line, the equation will return a value greater than 0 and the point will belong to a class called as class 0. But suppose the point is below the line, the equation will return a value less than 0 and the point belongs to class 1. So you have class 0 and class 1. There is one more term called as margin. What this margin indicates, it is the distance between the line and the closest data points. Okay, which is the optimal line? Okay, so the optimal line will be separating the two classes having the largest margin. That's why this is called as maximal margin hyperplane. So we have to select largest margin. Now, the points which are used in defining this maximal margin hyperplane classifier are called as the support vectors. So they actually support or define the hyperplane. There is one more term called as soft margin classifier. What is soft margin classifier? We are relaxing the constraints given to the maximal margin classifier, okay? Because real data will make it very difficult for us to create a perfect hyperplane. So soft margin classifiers are such with relaxed constraints, okay? So we'll be using few coefficients which will be creating a wiggle room in each dimension. Wiggle room in each dimension means what? Relaxing the constraints. So these coefficients are called as slack variables. There is a tuning parameter by name C, okay, that will be defining the magnitude of the wiggle. If the value of C is 0, there is no violation or there is no relaxation in the constraints. The larger the value of C, we are relaxing the constraints of the margin classifier. The data are the training instances that lie within the distance of the margin, which are affecting the placement of the hyperplane. They are called as support vectors. They are called as support vectors. SVM or support vector machine is implemented using a kernel. A linear SVM is an inner product of any two given observations. For example, let us say you have two vectors. First vector is 2 comma 3. The second vector is 5 comma 6. The inner product is 2 multiplied by 5 plus 3 multiplied by 6 leading to 21. Okay. So this equation for making a new production using the dot product uses this formula. F of x is equal to b0 plus I is summation of I is equal to 1 to 1 n ai multiplied by x into xi, where b0 and ai are the coefficients. b0 ai are the coefficients. X is the input vector, which is the new input vector. That this dot product is called as the kernel. This dot product is called as the kernel, which can be given as summation of x into xi. What exactly is kernel? It will be defining the distance measure. It will be defining the similarity measure. Okay. Now you also have variations of kernel called as polynomial kernel or radial kernel, and they are called as kernel tricks. The more complex kernel, the better. Now, if it is a polynomial kernel, it will be represented using this. K of x comma xi is equal to 1 plus summation of x into xi d. Okay, d indicates the degree of the polynomial. If the value of d is 1, then it is linear kernel. If it is radial kernel SVM, then it is indicated as k of x comma xi is equal to e to the power of minus gamma multiplied by summation of x minus xi square. The standard value suggested for gamma is 0.1, and it should be in this range 0 to gamma to 1. Now, how to learn an SVM model? You solve SVM model using an optimization procedure. The most famous method for fitting the SVM or solving the SVM is sequential minimal optimization. It is efficient because it will be dividing your problem into sub-problem, and it becomes easy for us to solve using calculations analytically than numerically. The data for SVM is, the assumption is data is numeric data. If the data is categorical data, you create dummy variables, okay? And you have binary classification in SVM. So let us take an example to understand this. This is our data set, okay? X1 and X2 are the two variables. And you can see your data set is divided into two classes. What are the two classes? Classes belonging to -1 and classes belonging to 1. So total 10 records are visible, and 5 records will be for class -1 and 5 records are for class 1. And you can see, you can easily differentiate between class -1 and class 1 data. Is it not? This is to make this, the author has given this separation, easier separations too, so that we can understand the problem easily. If we plot these points of x1 and x2 on the graph, you can see these blue labeled ones are -1 and the red labeled ones are 1, and you can easily segregate them and separate them. Okay. What is the goal of SVM learning algorithm? You should find coefficients. Which are our coefficients? These B1, B2 are our coefficients. Okay. Even B0 also is a coefficient, but in our example, we'll be keeping B0 as 0. So our new equation becomes B1 into X1 plus B2 into X2 is equal to 0. Now, finding these coefficients, the algorithm is called as quadratic programming problem. It is a constraint optimization problem. To find coefficients, you also use subgradient descent. Okay. So first, we need to calculate an output value using this formula y into b1 x1 plus b2 x2. Okay. Here, if the output value is greater than 1, then your training instance is not a support vector. If the output value is less than 1, naturally it's a support vector. Now, whenever such value comes greater than 1, you can use this formula b is equal to 1 minus 1 by t into b for updations, where b is what? B is a weight, okay, that is being updated for b1, b2. T is the current iteration. T is the current iteration. Okay. Now, if your training instance is a support vector, then you will be updating your B using this. B is equal to 1 minus 1 by T into B plus 1 by lambda into T into Y into X. What is lambda here? Lambda is a learning parameter. The suggested value for lambda is very small, like 0.0001. Now, let us take our first iteration. What is our formula? This is our formula, okay? So, initially, the B1 and B2 coefficients are kept to 0. This is our first iteration. And if you look at X1 and X2 first record from our training data set, you have X1 value as 2.32 something and X2 value is 2.45 something, and the class is minus 1. The class is minus 1. Okay. So X1 is 2.32 something, X2 is 2.45 something, Y is minus 1. So we'll be calculating the output using this formula, Y into B1 X1 plus B2 X2. We know the value of Y. Y is class is minus 1. Initially B1 and B2 are kept as 0. So 0 multiplied by anything is 0. So ultimately the output is coming to 0. This is less than 1. Okay. So now as it is less than 1, output is less than 1. We'll be using this formula because we have already decided which formula to use. Greater than 1, use this formula. Less than 1, use this formula. So we'll be using this formula, and we know we have kept the value of lambda as 0.5. Using this formula, we are getting the values of B1 and B2 as minus 5.17 and minus 5.46 respectively. So our first iteration is over. So let us move to the second iteration. In the second iteration, X1 value and X2 value is this. Let us verify that, 3 point something. So 3.03 and 3.17. This is in our second iteration. Okay. So again, using this, we are calculating B1 and B2. No, sorry. B1 and B2 we have already calculated, which is minus 5.17, minus 5.46. Now we'll be calculating the output using this formula, and we'll be getting the output as 33 point something, which again is larger than 1.0. If it is larger, we'll be using this formula and we'll be calculating B1 as this. Okay. After that, we'll be calculating B2 as this. Okay. This goes on for multiple iterations. Okay. You have to repeat this. One pass up on the data set is called as an epoch.
Sir, I have doubts. Sir, I have doubts, sir. I have doubts, sir.
Wait after I finish. For 15 epochs, for a total of 160 iterations. Okay. So if you calculate the accuracy, plot the accuracy of the model, you'll be getting like this. Now, after 16 epochs, we achieve an accuracy of 100%, and the value of B1 and B2 is settled to this. If I want to make new predictions, I'll be using this same formula. Okay. So if you look at this predictions and the actual values, the predictions are coming to be 100%.